In this case, which variable depends on which variable? X depends on y. What does y depend on? Nothing. So y is the one that's free, so I'm going to choose y to be t. And then the x will be cube root of t. Or you could write on your calculator t raised to the 1 divided by 3. And if you were to graph this, you would get the same thing as this. So parametric mode is more powerful than function mode because you can do both functions of x and functions of y and things that are neither functions of x or y, like circles. All right. So parametric curves are nice ways of drawing, is a nice way of drawing curves that extends past functions of x and y to things like circles. So let's talk about that area of that curtain now. We said that the area of the rectangle, remember I said was going to be this, right? That was going to be the area of that rectangle. We need to add them all up. Well, I'm going to switch x into a parametric equation. So my x is going to be replaced with whatever the function is that I'm switching to. So do you see right here? F of x of t, that x of t is my parametric equation for x. Then I'm going to replace my y with y of t. I think I need to go back one more slide to just make sure you understand what I'm doing here. In this picture, this curve on the ground, C, I'm going to draw that curve with parametric equations. All right? When I draw this with a parametric equation, then some point in that rectangle that I plug in to get the height is going to have the coordinates x of t, y of t. So that's the point I'm plugging in, and that's why this gets replaced with f of x of t, y of t. And then now I need to come up with the arc length part. Understand? Okay, so we are going to cut this thing up. This delta c is the arc length. And here, how would you find the arc length of the curve? So I'm going to draw a picture over here for you. Here's that curve C. If I'm trying to approximate this right there, right? Then I can draw a right triangle. This would be my change in x with respect to t, my change in y with respect to t. Right? So t is like a clock running in the background. As I move from one point to the other, the x and the y change, but they depend on t, don't they? Because I've changed them into the parameter t. So how much x changes by is with respect to t. This is an infinitesimal change in x. And then our y coordinate will change with respect to t also. By the Pythagorean, right, this will be the square root of this square plus this square. Okay, that's this right here. That's my arc length. And it's with respect to t. All right? So that's our formula. The key to the problem for us, really the heart of this is going to be, can you get a parametric representation of the curve? You've got to be able to get the parametric representation in order to use the formula. This is called, oh, I forgot to show you the notation. This is what we're doing here. This is the computation, but this is the notation for a line integral. And this is your first form. Is it the first formula there?
Yeah.
Yep. It is the integral over c. Now what's c? The curve on the ground, right? It's the integral over that curve of the scalar function ds. ds represents arc length. That's the standard notation that they use for it, ds. So this is called the line integral with respect to arc length. Later on, we're going to have line integrals with respect to something else, so the formula is going to change a little bit. I think we should do an example. I think it's time. All right, find the line integral with respect to arc length over that curve C, where C is the upper half of the unit circle, x squared plus y squared is 1. So we come in here, and the first thing we do is find your, what's that?
Don't you gotta find the scalar? Or is that already the scalar?
The scalar function, f of x, y, is right here. What we need to do is find the parametrization of the upper half of the circle. So how are you going to draw me a unit circle upper half only? You're going to let x of t be what? And you're going to let y of t be what? We just did this, right? What? Cosine t? Sine t? What are you going to let t be between? 0 and pi. Everyone hopefully agrees that that draws me the upper half of the circle. That will draw me, this is the parametrization of C, right? That's C. So what I'm going to do now, I think I'm ready for the integral. I don't think there's really anything else I need to do. I'm going to do integral from A to B. What's A, what's B? They're my restrictions on t, right? So I'm going to go from 0 to pi. And now my function, my scalar function, but I'm going to replace x with its function, right, of t, replace the y with its function of t. So this is going to look like 2 plus cosine squared t sine t, yeah? Y'all see that? That's 2x squared y. Then, what's the next part? The arc length part. Times arc length, which is the square root of, we need some derivatives here, don't we? Don't we? dx dt squared plus dy dt squared. So over here, I think I'm going to find those derivatives. What's dx dt? Negative sine t. And what's dy dt? Cosine t. And this is going to work out real nice for us, isn't it? Because when I put those in and square them, what's negative sine t squared? Just positive, right? And then cosine squared. And that just happens in this problem to be 1, right? dt, don't forget that. So that's 1, square root of 1 is 1. So we're there. This is equal to integral from 0 to pi of 2 plus cosine squared t sine t dt. Any questions on where any of that came from? We're okay? All right. And since this is our first example, I'll just take it the rest of the way, and plus it's pretty easy to integrate. So we're not doing double integrals here, right? It's just straightforward Cal 2 integral. Antiderivative of 2 is going to be 2t. Here we just do a basic u sub. U could be cosine. So what would the antiderivative of that be? See how good your integration is here. I know I've got 2t. What? No? 1/3 cosine cubed t. Take the derivative of that. What would you get? 3 would come out. Cosine squared t. Derivative cosine? Negative sine, right? But you need it to be plus, so minus right here. Do y'all know what I did? Do y'all agree? 0 to pi? Plug and chug now. So what happens when you plug in pi? You've got 2 pi minus, what's cosine of pi? -1 cubed. -1 times 1/3, that's -1/3 times, or minus, so plus 1/3. What happens when you plug in 0? 0, cosine of 0. 1 cubed, 1, -1/3, so -1/3 in there. And -1/3 minus -1/3 is plus 1/3. So you get 2 pi plus 2/3. Good enough. You can get a common denominator if you want, but just leave it like that. So that would be the area if you were to drop that curtain down. That's the first problem I showed you where we dropped that curtain. That's the actual area of that curtain. Questions, comments? All right. Yes. Mm-hmm. Yeah, so it's that first, well, I only showed you one picture, but it's that area of that green curtain right there. All right, so this is a result that we have. This allows us to, you know how like in Cal 2, if we had a curve and we wanted to find the area, we could break it up into 2 different integrals. Like instead of going from A to B, we could go like from A to C and then C to B. So you're allowed to break it up. That's what this is saying. It's saying if you have a curve C, which is the union of a finite number of smooth curves C1, C2, C3, Cn, then the line integral over that curve with respect to arc length is just the sum of the line integrals on each of the curves. So like in 2-dimensional space, which is the ground, if I have some curve that goes from here to here, which is C1, and then from here to here, which is C2, and then maybe from here there, C3, and then, stop it here at C4. Then these curves individually are smooth. Then what I could do is I could break this up into 4 different line integrals. Because drawing C1 might require certain parametrization of x and y, but drawing C2 might be a different parametrization. So I'm allowed, this is allowing you to split it up. I believe the next example shows that. So we'll look at the picture here in a moment. Find the line integral with respect to arc length of 2x, where C1 is the parabola y equals x squared from 0, 0 to 1, 1. And C2 is the line segment from 1, 1 to 1, 2. Let me try and draw what capital C is first. Let's start with C1. The parabola y equals x squared goes from here, 0, 0, to 1, 1. That's C1. C2 goes from 1, 1 to 1, 2. So just straight up. So let's try and come up with parametrizations for these curves. First, C1. What will your x of t be? What will your y of t be? So you want the x of t to just be t. So you're noticing that y equals x squared is like a function of x, right? Anytime you have a function of x, then x is free to be whatever you want it to be, and y depends on that. So you'll always replace the x with t, and then the y becomes t squared. Now you do need to give me some restrictions on t, though, because if you don't, this might draw the whole parabola, and you don't want that. So where do you want it to start? What's your smallest t value? 0. And that'll start you out at 0, 0, won't it? And then to where? To 1. So that when you stop, you're at 1, 1. And all the values in between should draw you the parts connecting this to this. Are you okay with that? All right, I agree. What's the parametrization for C2? You've done this before. You didn't realize you were doing it. What is that? Yes? Yes, yes. It's a line segment, right? How do we draw lines in Cal 3? What do we use to draw lines? Point and a vector, right? Point and a vector. We use the vector equation. Do you remember the vector equation of a line? R of t equals R naught plus TV. Remember that good old thing? Do you remember that when we did this, we could take the answer, we could convert it to its parametric equations and its symmetric equations? That there were 3 different versions? What did I say? Parametric equations? That's what we're going to do right now. We're actually going to find the parametric equations for a line segment. So let's see if you can recall how to do that. If somebody gives you 2 points, how do you come up with the vector equation connecting the 2 points together? I'll give you a hint. You've got to figure out what R naught is, and you've got to figure out what V is. So what's R naught going to be? Which point? Does it matter? If you're going to do this the way that I showed you in class, if you're going to go from one point to the other point, your R naught needs to be your starting point if you want this to work out right. So R naught's going to be 1, 1. Plus t times, now I need a direction vector. How do you get the direction vector? It's the vector that goes from 1, 1 to 1, 2. Again, you have to get the order right here. So what's the vector that goes from here to here? It's the vector 0, 1. Now let's put these together. This is 1, 1 plus, distribute the t through, you get 0t. And then add those two together, and you should just get the vector, what? 1 plus t. And what did I tell you for sure t would go between? 0 to 1. If you do it right, if you are going to connect 2 points together and you do everything as I showed you in class, t will guaranteed be between 0 and 1. Let's just double check it real quick. If t is 0, where are you?